take a look at this package. It says 8 cookies, 228 grams. Hopefully you can see that from here. How are they able to claim this? I mean, it's a little weird, right? They're clearly not identical. Slightly different shapes, slightly different amounts of chocolate chips, slightly different weights. In fact, we can check. This one looks to be about 30 grams, this one about 29, and this one about 24. That's already a 6-gram difference. And we still have a bunch more that we could weigh. So that's a lot of variability. And the thing is, the stakes are pretty high. If they shortchange this number by too much, that could be false advertising, which could mean some legal trouble. On the other hand, if they're too cautious and they're routinely overshooting that weight, putting too much extra, that's extra chocolate, extra dough, extra resources that are multiplied over millions and millions of these packages, and that adds up to a lot of money. So how are companies able to confidently promise something like 228 grams when every individual cookie is so unpredictable? And why does that promise typically hold up? Well, statistics. The company cannot control the exact weight of each cookie. There's variance, as we've seen. What they can control, however, is the process. And it's not that this claim is saying that each cookie weighs exactly 28.5 grams, 228 divided by 8. It's saying that the whole group of 8 will be very close to 228, right? The whole package here, all of these added together, will equal 228. That's a really big distinction. Some of these are lighter, some are heavier, but when we aggregate them, when we add them all up, their weights get surprisingly stable. Okay, so the big idea here is that when we take values like weights of cookies that have some amount of randomness, and we combine them by adding them together or averaging them, for example, too, that randomness starts to smooth out. Let's add up all of these and see what we get. Adding these up, we have 33 plus 29 plus 27 plus 24 plus 31 plus 28 plus 28 plus 29, which is equal to 229 grams. So even though the individual cookies varied anywhere from 24 to 33 grams, up to a 9-gram difference, the total weight of all 8 was only 1 gram off of the claim. That's pretty good. But it's actually even cooler than that, because when you start to do this a lot, say for thousands and thousands of batches of cookies, or in statistical terms, with many repeated samples, a really nice pattern starts to emerge. Let's try with a couple more. If I take another bag and weigh out the cookies, we'll see a similar amount of variation between individual cookies. But here, the total comes out to 232 grams, also pretty close. And then with this one, we also get 228 on the nose. Now, I'm limited by time and budget, so I'm not gonna buy out the whole grocery store and test this 1,000 more times. But coding is free, so we can write some code to simulate what would happen if I did take thousands of samples of 8 cookies. Let's take a look. As we add more packages to the simulation, we track their total weights on a frequency distribution. Different package weights along the x-axis, their frequencies along the y-axis. What starts to appear is something familiar, a bell curve. More specifically, a normal distribution. And this is part of what makes the normal distribution so important and so useful. Anytime we repeatedly take samples and look at their averages or totals, whether it's cookie weights or something completely different, the same pattern keeps showing up. Moreover, as long as the sample size is fairly large, this is going to happen regardless of the distribution of the cookie weights themselves. Maybe those cookie weights are normally distributed, maybe they're really heavily skewed, or even bimodal. The sums or averages of the weights in those samples will be approximately normally distributed nonetheless. Now, just how large of a sample you need to get that normality to show up is going to depend on how non-normal the original distribution is, but for large enough samples, the shape of the population distribution can be messy, while the shape of the sampling distribution of the mean still smooths out towards a bell curve. This is one of the core ideas at the heart of statistics. It's called the central limit theorem. More precisely, the central limit theorem says that if we repeatedly take random samples of a fixed size from a population with some true mean and standard deviation, then the distribution of that sample becomes approximately normal as the sample size gets larger, no matter what the original population distribution looks like. The center of that distribution is the population mean, and its spread, its standard deviation, is the population standard deviation divided by the square root of the sample size. So, if each cookie's weight has a mean of mu and standard deviation of sigma, then the mean weight of the total package of 8 cookies is approximately normal with mean mu and standard deviation of sigma over square root of 8. Importantly, this does rely on one additional assumption, which is that the observations must be independent. In our case, this means the weight of any one cookie does not affect the weight of another. Now, I don't know the particulars of this company's manufacturing process, but this seems reasonable that each cookie is formed separately, so we'll assume independence holds for sake of this video and sake of our example. This theorem is why companies can make reliable claims about totals, like 228 grams for 8 total cookies, even when the individual cookies vary so much. Now, technically, 8 cookies is a relatively small sample size. For the CLT to work well with this small of a sample, we are also relying on the fact that the individual cookie weights are probably already fairly normally distributed. If cookie weights were heavily skewed, we'd want a larger sample size, maybe something like 30 or more, but 8 should work well for a reasonably symmetric distributions like we'd expect here, and again, for the purposes of this video. Okay. So now that we know that these totals are well behaved and approximately normal, we can answer questions like this. What's the probability that a package of 8 cookies weighs within, say, 5 grams of the target? Suppose the company knows from years of production data that an individual cookie has an average weight of about 28.5 grams, with a standard deviation of about 1.8 grams. They don't know exactly how much any single cookie will weigh, but they do know the behavior of the process. Because 28.5 times 8 equals the 228, we expect the pack of 8 cookies to weigh around 228 grams on average. But we also have to consider the variability. According to the central limit theorem, the sample mean weight of 8 cookies is approximately normal with a mean of 28.5 grams and a standard deviation of 1.8 divided by the square root of 8, or 0.64 grams. If we want to talk about the total weight of the pack, that total is 8 times the mean. Multiplying a random variable by 8 also multiplies its standard deviation by 8, so that means we have a standard deviation of 8 times 0.64 equal to 5.1 grams. Okay, this means the total weight of our 8 cookie pack is approximately normal, centered at 228 grams, with a standard deviation of about 5.1 grams. Now, let's answer the question, what's the probability that a pack is within 5 grams of the target? In other words, between 223 and 233 grams. We can convert these to z-scores using the mean of 228 and a standard deviation of 5.1. Our lower bound will have a z-score of 223 minus 228 divided by 5.1, or about negative 0.98. And the upper bound will have a z-score of 233 minus 228 over 5.1, or approximately positive 0.98. If we pull up our Desmos calculator, linked in the description below, we can compute and visualize this on the graph. Plugging in negative 0.98 for our lower bound and positive 0.98 for our upper bound gives 0.67 or 67% for our area. So roughly 2/3 of the packages are within 5 grams of the advertised weight. Now, if the company wants, say, 99% of packages to meet a legal requirement, they can use this same framework to tune their process, maybe increasing the target slightly or tightening up the variability and so on and so forth. But let's flip the question and check if it works as is. Instead of starting with plus or minus 5 grams and asking what probability we get, let's start with a desired probability and ask what range of total weights will contain about 99% of all of our cookie packs. First, let's solve for the z-scores that cover 99% of the area under the normal curve. We have a whole video explaining how to do this in detail, so we'll just touch on it briefly here, but we can use Excel's norm.inverse function to find these. We'll first draw a picture, label our desired z-scores, label our areas, then plug the corresponding values into Excel using 0 for the mean and 1 for the standard deviation, since we're working with z-scores using the standard normal curve. This gives z-scores of about -2.58 and +2.58. Remembering that a z-score is essentially just the number of standard deviations away from the mean, we can multiply these by the standard deviation to put them in context of grams. 2.58 times 5.1 gives us 13.2 grams. So 99% of all cookie packs should fall within 13.2 grams of 228. 228 minus 13.2 equals 214.8, and 228 plus 13.2 equals 241.2. So we expect about 99% of all 8 cookie packs to be between 214.8 and 241.2 grams. Now, suppose the regulation says something like this. At least 99% of packages must be within 6% of the advertised weight. Does our cookie meet those requirements? Well, 6% of 228 is 0.06 times 228, or 13.68 grams. That gives us a lower bound of 228 minus 13.68, which is equal to 214.32. And that gives us an upper bound of 228 plus 13.68, which is 241.68. So our 99% cookie range sits safely inside that legal window, which means this process should comfortably satisfy the legal requirement. This cookie example is one instance of a much bigger story. Anytime you average or sum a bunch of independent, reasonably similar random effects, exam scores in a class, daily sales for a store, measurement errors in a lab, or even heights or blood pressure in a population, the distribution of these averages is pulled towards a normal shape with variability shrinking as your sample size grows. That's the central limit theorem at work. And it's the reason so many statistical methods rely on the normal distribution. Even when the world is messy on the individual level, the averages we care about are often close to normal, and that lets us quantify uncertainty, make predictions, and justify claims like 8 cookies for 228 grams with real confidence. I hope you found this video helpful. Have a great rest of your day.